Hi, I'm Jules, and this over here is Dulma. We're both engineers on the static analysis tools team at Facebook, and our team works on Infer, which is a static analyzer, which is open source. So we're sort of doing a tag talk here, where I'll start things up by presenting Infer and how it's deployed within Facebook. And then Dulma will take things over and talk more in details about how you can write your own static analysis checks using the new AL language inside Infer. So the reason that we're working on DevTools, I think, and in general, and more personally, the reason I'm interested in static analysis is that programming is incredibly hard. And in fact, I would go as far as to say that writing code of any significant size that has no bugs is practically impossible. And so to mitigate that, we develop best practices, but mostly we don't want to ship bugs to our users because this has consequences. First of all, the user experiences a buggy product. And second of all, the developers has to figure out a way to ship the fix to the user somehow. So instead, we want to prevent buggy code from shipping and ensure that the code base remains of good quality. And we do that, we want more specifically to ensure as the code is written that we give feedback to developers that the code is good enough to ship. And there are several ways to do that in the industry. So one is to implement code review. Another is to have testing in place so that, for instance, each piece of code should pass some set of tests before it goes into production. And what I'm going to talk about today is static analysis, which is another tool you can have in your toolbox to give signal to developers that their code is correct. So static analysis is a very broad term, and it applies to any tool that can give feedback on a piece of code just by looking at the source code without executing it. And so obviously this is very broad, and it can go from very simple things such as enforcing coding style, for instance, good indentation of your code, but it goes all the way to more complex checks, which is more what I'm going to talk about today, that try to actually understand what the source code is doing in order to find inconsistencies and potential sources of bugs. So Infer is such a static analyzer. It tries to build mathematical model of the source code that represents all possible execution paths in order to find issues. And I want to insist on two sort of specificities of Infer compared to other static analyzers out there. One is that it's interprocedural, so it's able to find issues that can span several procedures, sometimes located in different source files of your project. And the second one is that it's incremental, which means it's able to quickly analyze code changes. And as we're going to see, this is important for the way we deploy Infer within Facebook. So as I mentioned, Infer is open source, and you can get more information and get Infer itself at fbinfer.com. We have a bunch of stars on GitHub and many users within Facebook, but also companies outside Facebook using it, such as Spotify and Uber. So after this quick introduction, I want to give you sort of a flavor of what Infer can do by showing you some examples, some concrete examples on an existing app. So I picked the DuckDuckGo Android app. DuckDuckGo is a search engine, and they have this open source app. And so let's run Infer on it. To run Infer on a project, you take the compilation command of your project. So in this case, DuckDuckGo app builds with Gradle. And you just add infer -- in front of the compilation command. That's the easiest way to run infer. And here it will tell you that it found a bunch of source files to analyze, and it will crunch it, and at the end it gives you a report. And here we see that it found some resource leaks and other references. So let's look at one of the resource leaks it found. So the error message for that one is that there's some resource acquired by a call to the database at some line, and this resource is never released after some other line. So if we look at the source code surrounding this, and here we only need to look at the yellow lines, we see that there is a cursor allocated by a database query, and then there's an if condition. And if we don't go into the if, then we close the cursor and we return. But if we do get into the if, then nothing in here will close the cursor, and that's what Infer flagged here. Let's dive into another example, this time that spans multiple procedures. So here's another bug Infer found. It's another reference. There's some object that's assigned on some line, and Infer found that it could be null, and that it's the reference by another method call. So it's actually all in a simple two-line function, but it calls other methods. So this feed object is allocated by this call, and that's located somewhere else, and Infer analyzed it and figured out that it could return null. So, and if we go there to look at it, we see that initially it initializes the feed object to null, and then a bunch of things happen, but it could be that the cursor is empty and we never get to the line that changes the feed object to something else. And if that's the case, then we return null at the end. So at this point, feed object could be null, and now it feeds into another method. And if we go look at that method, feed item selected, we see in its body that in the first few lines, it will call a method on that object. And in Java, if the object is null, you would get a null pointer exception here. So that's what Infer flagged. It was able to track the null value across several procedures to give you a bug report. And it will also provide you this trace that goes across these procedures, so you can see why it thinks there's this null pointer exception. Okay, so I want to go over a few of the bug types that Infer finds, such as the one we just saw. So there's null dereference, but also memory leaks, which are like resource leaks, but when you allocate memory, that's never freed. And there are also retain cycles, which is some leaks that can happen in Objective-C, where you get references that point to each other in a cycle, and so that the garbage collector can never free. And there are other errors in this category, but I can't show them all. And another sort of category of errors is more language specific. For instance, trying to access an element of an empty vector in C++, or there's this thing in Android called context leaks. And in C++, again, there's static initialization order fiasco, where the order of initialization of your global object is not guaranteed and can lead to crashes. And finally, the last category I want to mention is more syntactic checks, sometimes called linters, which is not so much about understanding what the program does, but more about enforcing some constraints on the syntax just the syntax of the program. These are the coding style-like errors I mentioned, but they can be a bit more sophisticated than that. For instance, you shouldn't compare a pointer type to some other type, or you shouldn't use some API that's is not available in the version of your SDK. And Dulma will tell you more about how you can write your own checks in that category. Okay, so there are many more other bugs I didn't mention, but let's move forward to just a very brief overview of how Infer works under the hood. So Infer starts from a project, and a project is a bunch of source files and a way to build them. And so that's what you give to Infer. And Infer, so there are sort of three phases: the front end, the analysis, and the reporting phase. So in the first phase, Infer will try to capture the compilation process of your project and translate all the source files of your project into its own intermediate language called Scale. And this is much like a compiler. And this intermediate language abstracts away from the different languages into a common and much simpler assembly-like language so that the analysis can focus on a simpler language. So then the analysis kicks in once all the procedures have been translated, and it summarizes each procedure as a specification of what the procedure does. And that's where it attempts to prove that the procedures do not exhibit bad behavior, and when it cannot prove that this is the case, then it classifies the proof failure either as a weakness in the prover or something that's likely to be a bug that the user might be interested in and that we should report. And so once all the analysis is done, then we report. Okay, so now we have a static analyzer Infer. How do we deploy it? So more specifically at Facebook, so we have Infer and we have all these apps. So what can we do? Well, a naive answer would be easy. Let's run Infer on all these apps and get a list of bugs and try to assign them to developers so that they fix bugs, because who wouldn't, right? But it turns out if you do it that way, developers it will be too long after the fact that developers have written the code and they're not thinking about it anymore, and they're working on other features, and it's hard for them to see if they should prioritize this instead of working on new code. So this wasn't very successful at all. So instead, what we found successful was to integrate Infer inside the development process and give feedback at the time the code is being written. And this was much more effective. So in a bit more detail, a developer writes code and sends it for code review, and this is what happens basically at Facebook. The code review tool is called Fabricator. It's also open source. And when she sends the diff to code review, it also kicks in the continuous integration system, which runs the tests and everything, and also spins up Infer. Infer will analyze the code change at the same time that the reviewers are reviewing the code. So human reviewers give feedback on the diff. And at the same time, Infer also gives feedback. So just as a human reviewer, it will comment on Fabricator, adding a comment at some line saying, hey, I think you introduced a bug here. And that's how it's integrated. Never mind what it actually says. So at some point after that, the developer has updated her diff, and the reviewers are happy, and Infer is happy, and the diff can go to production. So I want to say just a few more words about how exactly running Infer at diff time works. So the way we do it is we run Infer on the top revision, so the revision with the changes, with the code change, and that gives us some set of issues reported by Infer. And we also run Infer on the base revision, the one without the change. So this provides us with sort of a baseline of existing issues in the code base. And then we compute the difference. And we're only interested in the new reports, and which means we only report issues that are likely to have been introduced by the code change. And that's very important to make sure that developers care about the feedback that Infer gives them, because it's actually about the code they wrote. So in a typical month, Infer runs on thousands of modifications of the Facebook mobile code bases. and hundreds of the issues reported by Infer are fixed by developers. And that's how we measure success. It's of the analyzer. It's how much do the developer care about the feedback that Infer gives them. And if Infer was not giving very relevant feedback, then they would never fix the issues that it reports. Or if it's not tuned well for the code base, or things like this. And these are things we saw at Facebook with other deployments of static analyzers. But with Infer, what we found is that developers actually fix 70% of the reports by Infer. So that's our main metric here. And now I will let Dulma tell you a bit more in more details about how you can write your own syntactic checks using AL in just a few lines of code.
Thanks. Hi, so I'm Dulma. I'm going to talk about how anybody can write simple checks with Infer. We developed a way of writing linters within Infer. So first of all, Jude told you how normally the way Infer works is that it is interprocedural. That means it finds bugs across several procedures, across several files. And the difference to linters is that those are more syntactic checks. They're often local to one procedure only. But we noticed at Facebook that we also want to be able to write linters in an easy way. So developers ask us for many checks, and they would like to have a framework where they can write it themselves in an easy way. So we developed a language for this. It's called AL. It stands for AST language. AST is the abstract syntax tree of a program. So it is a domain-specific language for writing linters, and it works by traversing the tree of the program. So it is for adding checks for syntactic properties of programs. So we have at the moment many checks deployed at Facebook that are developed with this language, in Objective-C in particular. So here are a few. We have a check for when properties have an atomic attribute that we are not accessing them directly, or when delegates have the attribute strong, that things that should not be done, or when a property has a type pointer and an attribute assigned that is like not very memory safe, or a register that has not been deregistered, some object that was registered and didn't get deregistered at the end. And one that people find quite useful on Facebook is checking that constants or methods that they're using is available in some API that they want to support. Like at Facebook in general, we want to support not the latest iOS, but also a few versions before. And so this is an automatic check to make sure that if you use this, all these APIs are not available that will cause a crash, then we'll let you know. So we have a few more. So another example of use of this language at Facebook is Component Kit, which is a framework for writing views that is developed at Facebook, but it's also open source. It's Objective-C++, and this basically inspired by React, and they're trying to be a functional approach to building UIs. So they have this framework, and many thousands of developers at Facebook use it, and so they wanted to have best practices to how to use the framework. And so they implemented this with AL as well. So they could be like, don't subclass components. The components should be more like composed, or the variables should be const as much as possible because they want the components to be as immutable as possible. And that has also been quite successful. So I'm going to show you an example of how one can write such a check. One of the checks I mentioned before, the assign pointer warning. So it is a class, my class in Objective-C, that has a property P of type pointer to other class, and it has this attribute assign. And so in general, we want to flag this as you should actually have an attribute strong or weak, which is more memory safe. So then we get ourselves familiar with the ST of the program. So this is how it would look like for this program. We have the nodes for the different parts, the interfaces, and the property. And in the property declaration, we can see the type and the attributes. And so we can basically traverse this ST and flag this. So this is how it looks in null. So we define the name of the check, assign pointer warning. We define a formula as to when it reports. So in this case, it's using predicates. It's assigned property, it's a predicate, and then a connector and then it's property pointer type. And also, it holds in a particular node in the property declaration node. And then we can write the message. It should be like the property, and the name of the property is a pointer type marked with assign attribute. And a suggestion, use a different attribute, like strong or weak, and the severity is a warning. And so we write this in a linters.al file, and we pass it to Infer with this option ---- linters def file in the file. And that's just all you need. And Infer will parse this and run it, and then you will have a new check for your code base. So more generally, this is how the checkers look like. So you define name, you define when to report the formula, and then a message, and an option or suggestion, and a severity. That could be one of error, warning, or advice, or info. So now I want to talk a bit about how the formulas are built in this language. So it is using CTL, which is a logic to express the properties of a tree model. And in this particular case, the model tree that we're talking about is the ST of the program. So this is how the definition of formulas look like. So we have predicates. We have not or are implied connectors. And then we have a few other operators for traversing the tree that I'm going to talk about a bit. So to begin with, let me tell you about the predicates. So these are written in OCaml. We provide a library, and then you can use those. And it still needs to be extended with many more predicates, but this is something that needs to be written in the OCaml side. And then, so here are some examples of predicates we have, like call instance method with name of the class and the name of the method, or call class method, it's the same. So for each of these strings, it can be a constant string or it can be a regular expression. And we also have support for types, something like has type for any expression or declaration. It has some particular type, or declaration has name for any name of any declaration, and so on. So now I'm going to talk a bit about the CTL formulas, a few of those, going through and explaining how they work. So for example, there's one holds in node, which is like I'm traversing a node, I'm in a particular node, and the formula holds here, so then it's true. Then holds next is there is one child of the current node where the formula holds, then this is true as well. Then holds eventually is there is a path where at the end of the path the formula holds. So that means the formula holds in the first node. Another one holds until is like the first formula F1 holds in a path all the way until another formula F2 holds. Yeah, I'm going to show only these ones, and there are a few more, and there's documentation on the website. You can get familiar with it. So another thing the language has is macros. So we provide these predicates, and with the predicates and with the operators, you can build formulas, but it doesn't need to be a fixed formula. It can be a formula with a variable, so you can reuse it in various ways. For example, here we can have this macro is subclass of, which is defined as something is a class and it holds in a superclass of a class node. And then you can use this for writing specific linters of checking about specifics of classes. So you can put this in the AL file, in this global markers part of the file, and also you can import it. So you can define the macros in a file, and you can import it into another file with the checkers, with this syntax. Now I'm going to show you a demo. We want to write a checker. So this is just small C language. We have an implicit cast from int to char. So Clang has a check for that. So we want to write the same one. So this is how we write it. We call it implicit cast. Report when. The node has type char. And a node inside the tree has type int. And this holds in the implicit cast expression node of the AST. And so for the message, we want to write the same that Clang was saying. Implicit cast loses integer precision from int to char. And for severity, we want to say it's a warning. So now we pass this to Infer with the linters.def file option. And we see the error. So now I want to show you how you can interact with it if things go wrong. So we made a mistake. So we said implicit cast, and so it doesn't find it. So we can put a breakpoint in a line of the program where we want to see what happens. And so we pass linters developer mode, and then we can debug through it. So we see that it's red, the node means the formulas don't work. So then we can fix it, and let's say we make a syntax error. So we see it crashes with syntax error, it tells you the line. And so then we fix everything and run again. We run the debugger again, and then eventually you will see that the node is green, and means that the formula is actually holding. So here at the end, in implicit cast expression, is green, and the formula that was being evaluated in the node is the full formula. In this node, implicit cast expression, this holds. And so it means your check is fine. Okay, so to conclude both parts of the talk, we talked about Infer, which is interprocedural static analyzer that finds bugs of many kinds in various languages, Java, C, and Objective-C, and C++. And we also mentioned AL, which is a domain-specific language for writing your linters. And so in fbinfer.com, you can find documentation, you can find a link to GitHub, you can download it. And yeah, we look forward to your contributions. Thank you.